Okay,
Hey, Kate,
so,
do you wanna join? We're making a group chat for like 8 minutes.
so I was informed that apparently the quiz grades aren't showing for you guys, so I will fix that. Sorry, I didn't even, it shows when I look at it. That doesn't really help you guys any, though, does it? So, I will see what's going on with that, I'll try and get that fixed. Sorry, I didn't realize, like I said, everything looked fine when I was there, but we'll get that squared away for you guys. And that should get that resolved. Next week, right, we'll have our last exam. We'll do it the same way that we did for exam 2 there, where, you know, we'll kind of, we'll do it online, and there'll be some stuff that you guys submit, and then you guys will submit your work at the end and that kind of thing, okay? So we'll open that up on Tuesday there. We don't have, you know, you guys don't need to go to lab or anything like that, right? So we'll be doing it online for that stuff too. What's up?
You said last exam, there's still gonna be another final exam. right?
Yeah.
Okay.
The last, you know, of the chapter exams, right? Then the final exam will be later. Okay, good. All right. So, we were making our way through the gas laws chapter here, and we were just kind of walking through the, let's say, the introduction to it, and discussing how and when and where and why and what are the different variables that we're going to run into and that kind of thing. And the main point that we kind of begin with here is just we're going to be dealing with what we call an ideal gas, and that just kind of, I guess, puts the math in context is what it is, okay? As we are all aware, and as I'm sure you guys already know, right, this isn't an ideal world, but if we do want to keep things as simple as we can to get the best estimate of things, so to speak, then we do have to make a couple of assumptions. And that's all we're doing with this, right? One of the assumptions is that, like we had on one of the previous slides, is that the gases, if they do collide with each other, they're completely elastic, and there's no transfer of energy and all this kind of stuff. So that's just kind of some methodology that we have for developing the equations, is all it is, okay? But one of the important things, I think, where we ended up is just discussing that we are going to be, any temperature that we deal with in this chapter, we have to do with Kelvin, just because Kelvin doesn't have any negative values and it doesn't have a zero that's going to be practically reached, right? And so that's going to be important because you're going to see a couple equations where we divide by the temperature, right? So obviously we can't divide by zero. That's just one of these rules of the universe, right? And so then we have to make sure that we use the appropriate scale there, okay? Anyway, one of the first laws that we kind of have to take into account is Boyle's law here, which tells us that volume and pressure are proportional, okay? And I think, again, this is kind of something that we already kind of knew or figured out or understood or something, whatever you want to say at this point, right? So volume and pressure are proportional, right? So as you increase pressure, volume is going to increase also, is all it talks about, right? And so that kind of makes sense, right? You know, when you think about putting more gas, right, more gas into a sealed container, right, there's going to be more, you're going to put more pressure on that system, right? So that's all this is really talking about here, okay? And this is kind of the one to pay attention down here at the bottom, and this is just kind of showing we how we get there, right? Volume is equal to a constant divided by pressure. We just rearrange, and then if there's a question that asks you to compare pressures or volumes at different conditions. So a question that says, if you have a gas at this pressure in this container, and you change either the pressure or the volume, this is the equation that we'll use here, right? But I'll show you guys another way that we'll get to that, okay? So we're just talking about under different conditions if we change pressure and volume. This is the equation that we'll be coming back to, okay? And we'll notice that we have to keep temperature and number of moles constant, all right? Because otherwise we have to use a different equation and a different approach for that, okay? Cool. All right, there it is. Move along to Charles's law here, and there it says that volume is proportional to temperature. Again, this might be something that maybe we already conceptually understand, right? The idea of heating, right? Heating a sealed container, and we talked about how temperature affects the kinetic energy of gases and their movement and their speed and all that kind of stuff, right? So again, volume proportional to temperature, we do our little rearrangement here, and we get our second equation that's important, right? And a way to compare how volumes and temperatures change at different conditions there. Yeah, what's up?
If absolute 0 is 0 on the Kelvin scale,
Yeah.
okay. So, what is 0 Celsius on the Kelvin scale?
What was it, 273.15?
Okay, so this is just gonna be, so is Kelvin
Is that what it is? I
equivalent?
forget now. I think that's what it is.
Yeah.
Is
Yeah.
Kelvin equivalent to Celsius in like the amount that each
Oh, there
degree?
it is.
Huh?
Like, is Kelvin and, are Kelvin and Celsius equivalent in like the amount of each degree?
Yes.
Okay.
Yeah, if you go up 1 Kelvin, you go up 1 Celsius. Yeah,
Okay,
yeah.
great, thank you.
Yep, yep. All right. So anyway, so here we have the second equation. If we're asked to compare volumes and temperatures under different conditions, that'll be the equation that we use there for that. Okay.
A lot of equations in this chapter.
Yeah, it'll come together to one of them, right? So we'll show that in just a minute. All right, so Avogadro's law, not to be confused with Avogadro's number, right? A very common kind of mistake there. So volume is proportional to moles. And again, this might be something, if we take a moment just to kind of think about what we're saying, is the more stuff you put into a container, the more space it's going to take up, right? So that's basically all it's saying there, right? But again, we have to keep temperature and pressure constant. And so if we think about this for just a second, for each of the 3 equations that we've been talking about here, we always have to keep some things constant, right? If we change 2 different variables, then we're gonna have to have a different equation to account for both of those things here, okay? But if we keep temperature and pressure constant, then all we can look at are the moles and the volume, and we can get some information out of that. This is gonna be important here, we'll come back to this and we'll come back to this thought, but any 1 mole of a gas at standard temperature and pressure. So whenever you see that STP there, what we're talking about is 0 degrees Celsius, or the appropriate Kelvin, and 1 atmosphere, okay? So that's just a definition of what standard temperature and pressure are, right? It's not room temperature, it's 0 degrees Celsius, right? So about 20 degrees lower than room temperature, and at 1 atmosphere, okay? And we'll come back and we'll talk about that in just a second. But the volume occupied is 22.4, okay? Cool.
I have a stupid question.
Okay?
I know this is probably just me still struggling to completely understand how moles work, but
Yep.
isn't mole basically like molecules of?
It's whatever you define it. So if you want to say I have a mole of those particular molecules, sure.
Okay, so are all gases like the same size or mass or volume or whatever?
No.
So how?
Volume maybe, right? Because well, if you're talking about like a container that you keep the gas in, right? Or are you talking about molecular volume?
Molecular, I guess, because how would 1 mole of H2, for instance, occupy the same amount as like a xenon?
How would it?
Like this is saying that the moles are the same size, right? Essentially, if 1 mole of any gas at STP occupies that much of a
Sure.
liter.
For an ideal gas, maybe that might be where you're, right? Under the conditions of an ideal gas, we will say they occupy the same space, right?
So what
Remember,
would be an unideal gas then?
things like water vapor is not an ideal gas, ammonia is not an ideal gas. These things that actually do have significant intermolecular interactions, right? So in reality, like probably helium is the closest real life example. Helium and nitrogen are probably the closest real life examples we have of ideal gases. There are actually interactions between some of these other ones, right?
Okay.
But they're just insignificant compared to the space that they take up, right? There's not a lot of interaction between them, but there could be some, I guess.
Okay.
Right, the differences also come from when these things actually do hit each other in space and the collisions and the middle, if you think about this for just a second, so the middle of a container, right? If you have a sealed container, if there's a gas in the middle, it's going to be behaving differently than a gas that's by the wall of that container, because we also have interactions with the wall.
Around them?
Well, we have access, it can bounce off the wall, which changes things and these kind of ideas here, right? So we're kind of building an ideal borderless container that doesn't have any interactions in it.
So
That-
something that doesn't exist.
Exactly, that's why we call it ideal, right? Nothing in this world is perfect, right? But otherwise, and like I said, at the end of these chapter, I'll have a couple of slides that say how do we actually account for a real life gas, right? Yeah, what's up?
So wait, according to that, the ideal temperature is 0 degrees Celsius?
Not the ideal, the standard temperature and pressure.
Okay,
It's just that when we deal with STP, right, there's just a definition that we have.
okay.
Yeah, the temperature could be anything if I define it. But if in a question I say, at standard temperature and pressure, calculate the volume of this, right? Then I'm defining the pressure and the temperature in that, by saying that, that's all it is, right? Just like when we say room temperature, right, we mean 25 Celsius, right, is what it is, okay? Although in the mornings in this classroom, it's not. All right. Okay? So, this slide here always kind of, I remember when I first kind of went through and started learning this, I'm like, what in the world are they talking about? But, so what we're seeing here, right, is at constant temperature and pressure, right? So the volumes of reacting gases are always in the ratios of whole small numbers. I was like, what in the world is, it's just stoichiometry, that's all I'm saying, okay? So, 2 liters of this plus 1 liter of that makes 2 liters of that. This is what we're talking about here, the ratio of the gases that come together, all right? So that again helps us just contextualize how we can approach these reactions practically, right? That's all we're really saying, because you know, we all might be familiar or at least have an idea of what it means to, you know, measure out 100 milliliters of a solution of something, right? So you get a beaker, you get a container, you measure it out, you put it together, you mix it up, and there you go, right? So the same kind of idea here, right? So we can just think of the stoichiometry as the proportion of the gases that are coming together, right? So they're always in ratios of whole small numbers, okay? And remember, just like what we talked about previously, volume is proportional to the number of moles, right? That's from exactly the previous slide there, okay? So that's what we're talking about here. So how can we rationalize the stoichiometry? Yeah, what's up?
How is the volume of like the oxygen essentially eliminated?
What do you mean?
On one side we've got 3 liters, on the other side.
Oh, why isn't 2 plus 1 goes to 3 liters? Is that what you're asking?
Pretty much.
Yeah, so remember here we're making a new molecule, right? So we're combining this with that,
Okay, so the
right? We're not
molecular-
saying that oxygen takes up 1 liter, we're saying oxygen gas takes up that 1 liter. And so now we make a new gas here, which is a combination of these 2 molecules there, right?
And yet it still ends up being exactly 2 liters.
Yes. If you are, that's fine. Then just think about it as stoichiometry, right? Ignore the whole gas and the liters thing, and then just think about the stoichiometry that we had before.
Right, like the equation I understand.
Okay, then just go with that. Although if that confuses you, then we need to have a different conversation too.
That's, I guess I just don't understand like how the volume essentially is like either growing or shrinking depending.
Well, we're not saying, again, maybe the best way that I think about it there is, right, the oxygen as a gas takes up 1 liter. There's not 1 liter, well, how do I put this? It doesn't mean that it retains that volume once it reacts and creates something new, right? That's what it's coming down to. We're changing what the molecule is. We're putting 2 gases together to make 1 gas out of it at the end.
So 2 moles of H2, okay, but didn't you just say that H2O doesn't follow the ideal law thing?
In reality, yes.
So that's just more hypothetical, that's actually inaccurate.
Sort of, right? Remember, hang on to those thoughts. I'll be happy to walk you through it. But let's get to the punchline here then. Okay. So this is the equation that kind of governs what we need to do here, right? The ideal gas law, right? Pressure times volume is equal to the number of moles times some constant R times temperature. Okay. So I think it might be on the next slide here or not, but there that constant has a lot of different forms. depending on the units that we're dealing with here, okay? So that'll be kind of one of the things to pay attention to. But all of these, if we combine them together, this is gonna be the ideal gas law here, and that's kind of gonna be our starting point, okay? And that'll usually be the equation that we kind of point to and say, hey, this is where we need to begin to break this stuff down, okay? Yeah,
So what's N stand for?
moles.
Oh, okay.
Yep, lowercase n is moles.
Because that makes sense alphabetically.
What do you want it to be? Lowercase m, and it stands for meters, right?
We just need a new alphabet.
Yep, there you go. All right. So here's just a smattering of the different units that we use, right? You'll see some things, right? Liters stay the same, right? Kelvin, moles, but we change from atmosphere to bars to temperature, right? Different units of volume here, kilopascal, right? So just paying attention to the units that it is. By far, we tend to use bar and atmosphere tend to be the two most common things that we end up seeing, though. Just for those reasons, right? You know, so those, I put that stuff here in case you guys are working some problems through the book and you need reference. If you go look this up in Wikipedia, I think they're up to like 30 different values that they have for the ideal gas constant here. And they have applications in different equations also, okay? So as you get to some of the different engineering courses or the higher level chemistry courses, you'll see that capital R there come back for different purposes too, okay? Yeah?
You said the torr is temperature?
No, toward, this is all pressure. Pressure, pressure, pressure.
Okay, because you said temperature when we got to that one.
Okay, that's temperature here.
Right, but the third one, the torr, what does that stand for?
Pressure?
I realize it's a pressure value.
Yeah.
Like ATM is atmosphere,
Yeah.
bar is just bar. What the heck is a torr?
A torr is a torr. I don't know if it has a longer meaning to it, I'm sorry. You might have to look that one up. But it's just another just like we have Fahrenheit, Celsius, and Kelvin, right?
Okay.
What do they stand for? Well, the name of the people who discovered it, right? So maybe there was a dude named Torr who's like, I need to name pressure after me, right? I genuinely don't know. There might be some longer meaning, I don't know. It's a good question, but no answer on my end, okay?
Thank you.
Yeah, of course. I'm glad to always help. All right, so first problem that we'll work through here is just kind of getting to that 22.4, all right? So remember that, you know, one of the previous statements that something to keep in mind is that an ideal gas at standard temperature and pressure is equal to 22.4 liters, okay? So let's see how we can kind of put this all into use here then, so to speak, right? So using the ideal gas law to, I should be very careful here. There it is. Okay, so using the ideal gas law, see if you guys can get to 22.4 there, right? So remember, we're saying that this is the volume, right? This is the volume that an ideal gas occupies, right? So if we take a minute to rearrange our equation here, nR is T over pressure, right? And we know that the answer should be 22.4, right? So let's see if our math works out properly. Right, let's see what information we're given, right? We have 1 mole, so N equals 1 mole, okay? By definition, pressure is 1 atmosphere at STP, right? So P equals 1 atmosphere. We're playing the game that we don't know what volume is, right? So that's what we need to solve for. And let's see what other. Temperature, right? 273.15 Kelvin. I remember standard temperature and pressure says 0 Celsius, but whenever we're dealing with ideal gas, I'll put it into Kelvin, right? And then R is based off of H2O, 57 liters, atmospheres, mole, Kelvin, right? So pay attention to what your units are there, right? If we're dealing with atmospheres of pressure, use the ideal gas constant, that's in atmospheres there. Otherwise, you have to convert atmospheres to torr, or whatever you might want to be, right? There it is. Okay? So when I approach these problems, that's what I do. I just make a list of the stuff that I know on the left-hand side. I just plug it into the equation and solve it on out. Yeah.
So for the R, the constant,
Yeah.
there will be like a list of it, like the list of those that we have to choose from.
Yeah. Right. But really, it comes down to just mostly it's what's the unit for pressure there. That's usually the one that swaps around.
So it's not like you can memorize that for, that's like not the same R for every problem that we do.
No, it can change, right? It's a constant in every case, right?
Okay.
It's a constant in every case, and so it doesn't change. It's just that one atmosphere is not equal to one torr or one bar, right? That kind of thing.
Okay.
So it's just, you could take this constant here and convert just like we convert any units, right? When the semester was easy at the beginning, you do a unit conversion and then you get the other value for R out of that as well.
Okay.
Yeah. What's up?
Is that T always constant too, or is that?
This is, I defined standard temperature and pressure, the STP up there.
Okay.
Okay, so if we back up for just a second. Here it is, right? So whenever I say standard temperature and pressure, I am defining 1 atmosphere and 0 Celsius.
Okay.
Temperature is, I will give you information about it, or you have to calculate it based off of other things.
Okay.
Okay? All right, so now that we have that all, let's see if we can plug this all together. Ooh. Volume, tank equals 1 mole. Okay, N by R here, 0.082057 liters, atmospheres, moles, Kelvin, temperature, 273.15 Kelvin, divided by pressure, in purple, 1 atmosphere. Cool. If you guys plug that in, hopefully we get right around 22.4.
Yep.
Cool. Okay, so if you're on an exam and you forget that 1 mole is equal to 22.4, even though I think I put it in that useful information table for you guys. But this is just where it comes from, right? So it's not an arbitrary number. It's literally just they plug it into this equation and that's the volume that they get out of it. Okay? So always a good idea, always a good practice to go through and check how units fall out. Moles will cancel out with moles. Kelvin's canceling out with Kelvin. And atmospheres is canceling out with atmospheres there, right? So we're left in units of liters, okay? Does that seem reasonable enough? Okay, remember the ideal gas law, we have 5 variables, sort of, not even 5, excuse me. We have 4 variables because R is a constant, right? So I have to give you information about 3 of those to be able to solve for the unknown. That's all it comes down to. So make your list, right? And then just see which one's missing and start to plug that in, okay? Good? Okay. See what you guys come up with. Be careful. Here, this is a little bit thinking about what we talked about before, right? Remember we said that basically when we're dealing with reactions, we can just treat our stoichiometry as we did with our moles, right? So I have 1 liter of oxygen in excess octane, right? What volume of CO2 will be produced? So basically we're saying how much CO2 is produced from 1 liter of oxygen, right? There's an important word in this question, isn't there?
Excess.
Yeah, so what does that excess remind you? I know we've been stuck in drawing world for a little bit here, but what is that term excess?
It tells us that oxygen's a limiting reactant.
It tells us that oxygen is not the limiting effect. Oh, I'm sorry, yeah, the limit, sorry, I confused myself, excuse me. I'm a dum-dum. There it is, okay?
That was a term from
Yeah, sorry about that. So it tells us that oxygen's limiting, right? And the other one has to be the excess reagent. How would this problem change if I didn't tell you there's an excess of something? We'd have to treat it as a limiting reactant type problem, right? You guys remember how to do those?
No.
Uh-oh. Okay. So those are one of these important questions. It might show up on exams testing your knowledge from the entire semester. Who knows, right? You guys catch what I'm saying with this? Subtle hints here and there. Right? So anyway, so how do we deal with this? So what are we trying to do? We're converting liters of O2 into liters of CO2. What if I had asked you the question, how many moles of CO2 would get produced from 1 mole of oxygen? How would you guys approach that?
Grams to moles.
Well, we're already in moles, right? So all you guys would do is convert what? Moles into moles using our stoichiometry. So how are we going to treat this? The exact same way, right? That's all it's saying. Okay? So the way we set this up is we have 1.0 liters of O2, right? For every 25 liters of O2, we have 16 liters of CO2.
Is that an asterisk or a plus sign?
Multiply there.
Thank you.
And 0.64 liters of CO2 get produced in this case. Okay. Not too bad, right? I like this problem just to kind of conceptualize how we can use stoichiometry and also to knock the rust off of the idea of limiting and excess reagents here, okay? So we're back into stoichiometry world. All right. One other thing to kind of think about here. If we take and we rearrange the ideal gas law for just a minute, right? So basically we divide by volume and pressure and right, and just rearrange, and then we multiply by molar mass. What we get into is an interesting equation here, right? That density, right, is equal to pressure times the molar mass divided by our constant in temperature, okay? So we have a way of relating density to the molar mass of an ideal gas. That's what this is telling us, okay? So when you're working through the book and they have a question of identify which gas this could be, okay? You're gonna have to use this equation here, because this is a way that we can relate all these gas constants to the molar mass of something. And if you know the molar mass, then you can kind of figure out what gas came out of that, right? So if they have you a question of identifying an unknown or something like that, this is the equation that they're asking us to point at with this one, okay?
Where does the D come from?
Good question, right?
Oh,
So,
density is mass over volume. No.
yes.
Yes?
Mhm. So, great question. So let's take a look at this. Let's take a look at this for just a second, right? I'm just going to expand the units here that we have, right? So moles, right? And molar mass is grams per mole, right? Volume is volume, right? So we pick whatever unit we want there.
Grams
Right?
over.
Okay. So if I'm looking at this side of the equation here, right? Moles, grams per mole, and volume. If I take a look at my units, moles canceled with moles, so we're left with what?
Gram over volume.
Grams over volume. So mass over volume. And mass over volume is equal to
Density.
density. Got it? So that's all we're doing here, okay? Good?
Yep.
Okay. And here's just a little bit more, just to kind of prove the point, I guess. And so we talked about SF6, and I actually looked at some videos the other day after I mentioned that in class. There's actually a really cool, like 20-minute video of some guy doing a bunch of experiments with SF6. He's a bit of a spaz, but but he does some cool stuff. Like he fills up an aquarium tank with SF6, and then he puts a cup in it and he starts drinking it. Right? It's interesting, right?
And then did he have to stand on his head?
No, he blows off enough hot air that it just comes out anyway. So.
Was this Mark Rober?
Huh?
Was this Mark Rober?
I don't remember the guy's name. He has like a huge YouTube following, right? You know. No, what do I know, right? But it's actually cool. I'll post a link for you guys. But it really is a super cool compound to look at there with that, right? But extremely dense, right? About 6 times more dense than air, so that's pretty unusual there. Okay. All right. Aha, the combined gas flow. Okay, so here's kind of where I start to. Here's kind of where I always pick up with things. So a lot of the questions that we come up with in this chapter are, okay, we have a gas at this pressure and at this temperature, what happens if we change volume? Or we have a gas at this temperature, what happens if we change pressure, right? So a way of relating changes to the properties of that gas, right? What happens as we change pressure, or we change temperature, or we change volumes, or we decrease the amount of moles, right? And how does that affect the values of that gas, okay? And so that's what we mean by the combined gas law. Here's what I mean. If I take my ideal gas law equation and simplify it, right? So put it all the way on one side, so PV over nRT, right? So I divide by nRT, okay? If we have our initial conditions, okay? So our initial conditions for whatever we're looking at. And remember, when we're describing a gas, right, we're using the gas law here. Okay? Our initial conditions can be related to our final conditions, P2, V2, over N2, R2, and T2. Okay? So the conditions at the beginning versus the conditions at the end. P initial or P final. Temperature initial, temperature final. Right? Just add whatever 2 conditions we're looking at. You guys with me on this one?
Mm-hmm.
Right? Let's simplify the equation for a bit. How does a constant change?
Not much.
Right. In fact, it doesn't change at all, right? So we can just kind of get rid of that because it's a constant, right? And so to simplify, P1, V1 over N1, T1 equals P2, P2, N2, T2, okay? So this is kind of our overarching equation that'll control as we change things. All we have to figure out is what is held constant and what changes, and we just plug it into this equation here, okay? Good? Okay, I've talked for a long time. So using this here, right, so using that, figure this out. Figure out what's held constant or what changes, and plug that in.
I'll lose that ball.
Not too bad, right? Seems too simple. I want something more difficult. Good. I'm just gonna solve it. Exactly. Yep. So it's just a relationship of pressure and volume. So pick a number. 5. Oh, you could, right? And then how does that mole change? Nothing. So what's it at the end? It was 5 at the beginning. So it's a constant. So you can get rid of the fraction. Okay. Alright. What would it? It's big enough. Okay, how's that change? It does, so if it's 5 and 8, we'll have to do it. Yeah, so you just, make it harder. Alright, sounds good. Does it change? Okay, yeah. No, if it's a constant, right, you can put all that stuff in there, right? You can pick whatever value, don't change it, but then it's not gonna change your answer. Okay? Cool. So P1, V1, right, over N1, T1, P2, V2, N2, P2, right? So what information? A gas occupies that volume at that pressure. Right, so P1 equals 1.00 atmospheres, V1 equals 401 milliliters, right? Then we do something, it says its volume if the pressure is decreased, right? So pressure 2 is 0.750 atmospheres, and it asks what the volume is, right? At constant temperature. Okay, well that's good, it tells us the constant temperature, so we can get rid of that, we can get rid of that. Okay? Is there a reaction going on here?
No.
No. Are we adding anything into this? No. So what does that mean about our moles? They also remain constant, right? We just have a gas in a sealed container and we decrease the pressure, right? That's all it says. So that's a constant also. So we can get rid of n. And now we have an equation with 4 variables, right? Do we have information about 3 of them? Yep. Can we get that one solved? Well, 9 a.m. on a Friday, we can probably do that, right? Okay. And so if we plug that all in, I got V2 is equal to about 535 milliliters. Good? Does this equation look familiar to something? Right? So if we scroll back in our notes, right? See if I can find it real quick here. Right? That's just Boyle's law, right? And what does Boyle's law say? Temperature and moles must be held constant, right? So remember the way we constructed the ideal gas law was based off of Boyle's law and Avogadro's law and Charles's law, right? So we should be able to back those back out as long as we hold the appropriate things constant. So that combined gas law is just our way of backing out these individual laws from that. So you don't have to memorize the individual ones unless you want to, or just approach it the same way we did with that problem there. Okay? I don't know, I have trouble remembering individual, a lot of different equations, but I can remember the combined gas law there. Okay, go for it. So now, well, I'll give you guys a second to copy down before I start talking again. What's up? Hmm? It is. Where are you getting that from?
R. Oh, I forgot to write the rest.
How are you getting this here? So be careful, right? So go back, write out the information that you have here first before you just start pointing at things at me. So what information am I giving you? So, real quick, while you guys are thinking here, what's different about this problem than the one we just worked? So for this problem, notice I'm giving you information about a gas at a set of conditions, right? Am I changing anything? Am I saying I'm increasing pressure or temperature, any of this stuff?
No.
No. So what equation do we need for this? Just PV equals nRT, right? When I have to use a combined gas law is when I'm saying we have a gas that starts at these conditions and then I do something to it, right? So to take a snapshot, so to speak, at a specific set of conditions, all you need is PV equals nRT. Got it? You guys catching what I'm saying with this? This is a good way to, this chapter can get confusing, but think about it like that, right? If I change the temperature or whatever, then we need the combined gas law. If it's just at a snapshot, then just PV equals nRT. Okay?
So, for ours, we just use the same number that we used.
Yeah, we're in atmosphere, so just pull that R that we had before. So 0.08206. Well, I'm asking what the volume is, right? So any measurement of, but it's gonna, the question then is gonna be what are the units for this back for your constant here, right? Right, so that's gonna define what the answer is. Right, because take a look. looks of the units here, liters, atmospheres, mole Kelvin, right? So here we have degree nodes and atmosphere, right? Yeah, exactly, and don't forget, whenever you do a problem in this chapter, you just. What's it mean if the decimal place in somewhere decimal place up there? Oh, so what are your units for this value? So go take a look at that and think about that right there. Okay. So what are your units for here? What is it, liter atmosphere, what's that mean? So, 273, at 273 too, okay. Cool, all right, we're getting a lot of the correct answers, but I did trick a couple of you guys, which I appreciate. I always like a good track, right? Remember, one of the most important things that's often missed is the conversion of Celsius into Kelvin, okay? I know we're used to dealing with Celsius, and I understand, but remember, for this chapter, put it all into Kelvin, okay? So moles, right? Enough of that information there is. I have information about pressure, right? Atmospheres. Temperature, right? So I'll go ahead and convert that, 304.15 K, right? So just add 273, right, to your Celsius to get from Celsius to Kelvin. Okay? And we need to figure out volume, right? It asks us what volume, right? And then we have liters, atmospheres, moles, Kelvin, okay? So just like I walked you guys through previously in the semesters, your best friend here is going to be writing out your units. Dr. H, do you realize how many fractions of calories it takes to write out this? Okay, what promise did I make you guys? I will buy you donuts if it comes down to an issue of calories to write out units, okay? I know you guys don't want to do this. It takes time. It's a habit that's going to help you guys in all of your other science classes. I promise. Promise, promise, promise. So just get in the habit here, okay? Because then, right, if we have our units here, we can check, right? Liters is what we're going to get our answer of volume in. Atmospheres is what we're given, right? Moles, got it. Kelvin, and we have our conversion to Kelvin, okay? So it's a great way to make sure you're on the right path before you start this out. All right, we start with our PV equals nRT. We rearrange to solve for volume, right? nRT over P. And then we can start to plug everything in. So volume was in black, so let's try and keep this all together. Volume, 2.64 moles, right, for N. Or temperature, it ran out of room, so let's see if I can do this. Fantastic. 304.15 Kelvin over pressure, 0.640 atmospheres. Phenomenal. Ah, thank you. That's it. That's the confidence boost I need. Yeah. So I got about 103 liters is what it is. Okay? Yep.
What am I doing wrong to get this with my,
So what are you trying to do here?
I'm trying to use the 1 mole equals 2.4.
Great question. So,
That, and it's not working.
right, so the question is, well, hey, wait a minute. I remember that you told us a shortcut. And you said that if I have 1 mole of an ideal gas, it's 22.4 liters, right? What's the condition for that? 22.4 at 0 degrees Celsius and 1 atmosphere, right? So don't get tripped up by that, okay? This is not standard temperature and pressure conditions, okay? I like the way you're thinking. You're like, I want to save calories, right? I don't want to take the long way. All right,
I just was trying to use it as like a check to see if my.
it's all good. But here's a question that does indicate STP. So now we can go through, right, with your thoughts. Pretty complex problem here.
Isn't O2 our limiting agent?
I don't know. I guess we'll just have to see.
Well, in the last one where we had this reaction, you said that O2 was limiting.
So a completely different question. That's what I said.
Is that not true here?
Huh?
Is that not true here?
We should never make that assumption, right? We should always read what the question's asking and then see what information we can get out of it.
The Carnot combustion equations, you're supposed to assume that oxygen is readily available.
That's a fair assumption to make, right? But maybe not always the case either. However, that one you just had a question, right? You can't do it directly though, right? You have to do a little bit of a shenanigans in between there.
Yeah, my brain just doesn't want
That's okay. Yeah. Where are you getting that from?
Oh,
Yeah,
yeah, okay.
yeah.
Just give me a second.
One step ahead of you there, but yeah, you got the right idea.
You have to kind of work the breaks.
Right.
And the octane is this agent.
Oh, yeah, I'm sorry, yeah, that's, yeah. The C8 is octane, yeah. That's a big shocker. It runs into moles, right? Mm-hmm. Kind of, but be careful, right? Because, this is based off of how many volts, right? Right? So don't skip steps. You will need that at the end, but you gotta do some stuff before you get there. What did you do? So what do we think? Good. What do you have grams? And then you need molar mass. You need to figure out the molar. You need to figure out the molar mass. Yep. No, not yet. That'll come later. All right. Slowly making our way back into math mode here, huh? So 100 grams of our octane here, C8H18. Remember, one of our principal things that we learn in Gen Chem is that to convert grams into moles, right? Moles are the things that we can compare things and put into equations and all that kind of stuff, right? So to convert grams into moles, we need to know our molar mass. So if we do that, we have about 0.8754 moles of octane. Okay. You guys remember how we got this value here? Okay. So there's our molar mass. Now we've got moles of octane. Okay. Now what do we have to do? What's the question asking us to do? At the end it's saying what volume of oxygen will be consumed, right? Can we convert moles of octane into moles of oxygen? Yes, we can, right? How do we convert moles of one reagent into moles of another? We need to know our stoichiometry. Also known as stoichiometry. Okay, 0.8754 moles of our octane. For every 2 moles of octane, I need 25 moles of O2, right? 10.94 moles of O2. And now what? Can we convert moles of O2 into liters of O2? We can, right? Either using the ideal gas law, or I define STP. So here's something to point out. I could have asked this question without defining STP, but giving you guys specific temperatures and pressures. And you would take moles and plug it into the ideal gas law, right? Remember, that's just N. We can plug it into our gas law. I did give you temperature and pressure information though, right? That's just what STP says. So I'm simplifying the math for you. But there are some problems in the book where they don't say it's STP. You approach it the exact same way, but you just plug it into your ideal gas law equation, okay? Don't get confused just because they throw a lot of numbers at you guys, right? Take it piece by piece. Eat the elephant, right? So to convert moles of an ideal gas at STP to liters, there I use my 22.4 and I got 245. Okay. Good? All right. So I will see you guys on Monday, and I'll get those grades fixed for you guys there. I'm sorry that wasn't showing for you.